Welcome back, Leo Lions. This is Mrs. Morgan with today's lesson over linear and nonlinear functions. So what are we looking for in order to classify them into these different categories? So everything we do today, they are going to be functions. We don't have to identify whether they are or aren't. I'm already telling you they are functions. But now that they're in the function category, well, then we need to identify, are they a linear or nonlinear function? So linear, obviously, it's in the word. We want to see, does it form a straight line? So linear forms a straight line on the graph. So first of all, we've been talking about slope-intercept form for a while. So anything that's in the form of y equals mx plus b, we've put it on the graph and we've seen that it forms a straight line. So anything in that form is going to be a linear function. So let's take, for instance, an equation, y equals negative 2x minus 1. All right, so we know now that over on the graph, we would start with the y-intercept, plot a point at negative 1, and then our slope would be down 2, forward 1 for negative 2, or we could go up 2, backwards 1. So if we were to actually draw that equation on the graph, well, it forms a straight line. It's a linear function. So if we actually have a graph, it's easy to just look at the picture. Is it a straight line or not? If we just have the equation, what we want to make sure is the line or the equation must be able to go into the format y equals mx plus b. And then we know that it is linear. Now, let's actually create a table here to then be able to look at, if we're just given a table, can we identify if it's a linear or nonlinear function? So let's take, for instance, our x value is negative 3. Well, what we're doing is taking that negative 3 and plugging it in for x. So negative 2 times negative 3, since they're right next to each other, that's positive 6. 6 minus 1, the y value is 5. So our input is negative 3, our output is 5. Do the same thing with all of these. So negative 2. Negative 2 times negative 2 is 4. 4 minus 1, our output is 3. Plug in negative 1. We get positive 2 minus 1 is 1. And I'm just doing this over and over. I'm putting it into our equation. So plug in 0 for x. So negative 2 times 0 is 0. 0 minus 1 is negative 1. Plug in 1, so negative 2 times 1, then we get a negative 2 minus 1, so we get negative 3. Now, hopefully, you guys can kind of see what is happening in our pattern, in our table. So if we're just given a table, well, we want to look at what's happening between the x and the y values. So from negative 3 to negative 2, each time we're adding 1 in our x values. Plus 1, plus 1. We're doing the same thing over and over. Now we're going to do the same thing and look at our y values and what's happening here. Well, 5 to 3, we subtracted 2. 3 to 1, we subtracted 2. So notice the same thing is being subtracted or added over and over. Then this is a key sign that this is a linear function. If we didn't have the equation or we didn't have the graph, we could just look at this table and see, okay, there's a pattern. We're adding this, or we're adding or subtracting the same number over and over, okay? Now, a verbal description of what's actually going on here. So as x increases by 1, so each time that we add 1 to the x value, as x increases by 1, then y decreases by 2. Okay, now we're going to be looking for a couple things once we have linear functions. So we have what we call an initial value. An initial value is where we're starting at. So the initial value in an equation is simply our y-intercept, so negative 1. On the graph, our initial value is where does it start out on the y-axis, so that's negative 1. In our table, it's where x equals 0, then what's our y value? There is -1. So in all of these, the initial value is -1. So I'm going to have you write down because we're going to have to identify initial values. And initial just means the starting. So initial value, here is our initial value, and then also over on the graph, our y-intercept, okay? Now, the other thing we're going to have to identify is what we call the rate of change. So in our equation, the rate of change is -2. If you notice in our table, -2, -2, so on, over and over, so our rate of change is -2. If you look at our graph, well, we could just find the slope. We would go down 2, forward 1, -2 over 1, down 2, forward 1. So this is what we call, the same thing as slope is called rate of change. And again, I just showed you how you can pull that out of all 3 examples. Out of the graph, find the slope. Out of the equation, it's simply the number in front of x. And then in the table, it's that pattern, that number that is being added or subtracted. In this case, subtracted over and over. Rate of change. I'm going to abbreviate here, okay? So sometimes we look at maybe an equation and a graph and we compare and say, okay, well, here's one person's speed, here's the other person's speed. Who has the better rate of change? Who has the better or the higher initial value? Okay, let's look at another example, because unfortunately not all of our equations are in slope-intercept form. But if I give you an equation like -x plus 2y equals 4. So you may look at it and say, well, it's not slope-intercept form, it's not linear. But if we rearrange this, we're learning in class that we can add this x to both sides. And I'm going to go over here to show you that we get 2y equals x plus 4. Since we added it, the x is positive. And then we'd want to divide by 2. And we could actually rewrite this equation and get it in slope-intercept form. Remember that there's really a 1 in front of that x. So we would write this as 1/2 x, and then 4 divided by 2, so plus 2. Now we just got it in slope-intercept form, so now we see it's linear. So we have to be careful, because not always do we look at the original equation and see the slope-intercept, okay? Now we could actually graph this. So positive 2 is the y-intercept. The slope is up 1, forward 2, up 1, forward 2. Or we could go down 1, backwards 2, down 1, backwards 2. So here, if we plot that equation, we see, oh, it's a straight line, it's a linear function, okay? Now, let's plug in our x values. So let's start with 0, because anything times 0, 1/2 times 0 is 0, and then we add 2. If we put in 1 to here, 1 times 1/2 is 1/2. Anything times 1 is itself. So 1/2 plus 2, then we get 2 and 1/2. Plug in 2. So half of 2 is 1. 1 plus 2 is 3. Do you guys see the pattern? Plug in 3. So half of 3 is 1 and 1/2. 1 and 1/2 plus 2, we get 3 and 1/2. So each time we're adding a fraction of 1/2. 1/2. So that would help us then when we go backwards. -1 times 1/2 is -1/2, so plus 2, we'd get 1 1/2. -2 times 1/2 is -1. -1 plus 2 is 1. And then the last one we'd get 1/2. Okay, again, we can see that pattern, plus 1/2, plus 1/2, plus 1/2. Okay, and then we can see how all of these things are the exact same. So I'm going to keep my consistent. So up above I did my highlight of blue with my initial value. So my initial value in my equation is the y-intercept. Y-intercept on the graph. And when x is 0, notice all of those. So the initial value in this example is 2. So I'm going to write off to the side here initial value equals 2. Now let's take a look at the rate of change. So I'm going to keep it again consistent with my orange. So rate of change is the same thing as slope, 1/2. And notice plus 1/2, so on, all of those. So rate of change is 1/2. If I look at my graph, we'd go up 1, forward 2, up 1, forward 2. So the slope is 1/2. So our rate of change is 1/2. Okay, and then a description in words for this is that as each time x increases by 1, so as x increases by 1, y is increasing by 1/2. Okay, so those are examples of linear functions. Be able to identify from all types of those examples, an equation, a table, and a graph. Now, the second page, let's look at some nonlinear. I'm just going to show you that if we have an equation where the variable x is the exponent, we're going to see that it does not form a straight line on the graph. I'm going to start with 0 again. Anything to the 0 power is 1. We're going to learn that in the next bundle. 2 to the first power is 2. 2 to the second power, 2 squared, is 4. 2 to the third power, so 2 times 2 times 2 is 8. So you can kind of see there's a pattern for sure. 1 to 2, we're going to multiply by 2. 2 to 4, we're going to multiply by 2. 4 to 8, so on. So we have to keep that same thing going towards the negatives. Again, we're going to learn this in our future classes, but 2 to the negative first power is 1/2. 2 to the negative second power is 1/4. 2 to the negative third is, just 1/8. And again, it's going to keep that same pattern. We're multiplying by 2. So if we were to graph these all over on the graph, so 0, 1, 1, 2, 2, 4, and I'm going with my positives first. 3, 8 would be way up here and fall off the graph. Negative 1, 1/2. Negative 2, 1/4. Negative 3, 1/8. So you notice, you can see here that we've got a curve to our line. It does not form a straight line. So as x increases by 1, y is multiplied by 2. So now we know that if we're looking at our pattern and we see anything being multiplied or divided, that it's not going to form a straight line. It's going to increase or decrease too fast, and it's not going to have a constant rate of change. So as x increases by 1, the y is multiplied by 2. So it forms a nonlinear function, okay? Again, in this example, I'm going to show you that if we have an exponent higher than 1, if we have x squared, x cubed, x to the fourth, any power on x, it is going to be a nonlinear function. So that's a way to identify just from the equation, is it nonlinear or not? If we plugged these values in, we would get -4 for 0. Plug in 1, 1 squared is 1, 1 minus 4 is -3. So each of these, I am just plugging in that value to my function up top and then solving for y. And I'm going to quickly do it here. Now, if we plot these points, we're going to see that we're actually going to create what kind of looks like a U. And we call this a parabola. And if you notice, around that y-intercept, it's symmetrical. So if we were to fold at the y-axis, you see that it just lies right on top of each other. It's definitely not a straight line when we graph it on the graph. And then in words here, I'm just going to say that the x values are symmetrical, or sorry, the y values that we got are symmetrical, meaning if we fold at that line, they're going to be the exact same, and it definitely doesn't form a perfect straight line. So those are some examples of nonlinear, and then we also have linear on